Hello everyone, my name is Cansu. We will talk about the topic of Facile production of cesium lead bromide single crystals in a hydrobromic solution. My presentation consists of introduction, motivation, methodology, results and discussion. First of all, I would like to talk about the general usage areas of highlight perovskites. Since highlight perovskites have excellent photophysical and optoelectronic properties, it finds many usage areas such as solar cells, photodetector, LED, laser and quantum dots. The areas of use we are interested in within the scope of the study are X-ray and gamma-ray detectors. Since cesium lead bromide has a large absorption range, it can interact strongly with high-energy photons. For this reason, it has been a popular material in detectors in recent years. The need for room temperature operated X and gamma ray radiation detectors is becoming more and more important every day, not only for scientific purposes but also for our society. For example, radiation detectors may be used in nuclear imaging, radioactivity monitoring, security and are hence very important for the welfare of modern society. What properties should X-ray and gamma-ray detectors materials have? It should have features such as high resistivity, high sensitivity and high spectral resolution. Cesium lead bromide has these properties. Not only perovskite structure are used in detectors. If we give examples of materials used other than perovskite, cadmium zinc tellurium, lead iodide, mercury iodide, and amorphous selenium. Cadmium zinc telluride has promising applications due to van der Waals gaps between the layers. Perovskite materials have a common structure called AbX3, and we are cations with different sizes. The A cation is larger than the B cation. X is an anion that binds to both. Each A cation is surrounded by a 12X anion in a cubic octahedral coordination, and each B cation is surrounded by a 6X anion in an octahedral coordination. Within the scope of the thesis, we will synthesize cesium lead bromide in single crystal form in which all unit cells lie in the same direction. The majority of devices are based on polycrystalline thin films that suffer greatly from grain boundaries. Compared to polycrystalline thin films, single crystals provide better lifetime, better defect tolerance, and better carrier mobility. Polycrystalline thin films with higher defect density and trap density cause disadvantages when integrated into devices. If we look at the change in the number of articles about perovskite over the years, we see an increasing trend. It has accelerated in the last 5 years. When we examine the perovskite subject as hybrid perovskite and inorganic perovskites, we see that completely inorganic perovskites have been studied since 2010. Compared to hybrid perovskites, it has more aspects to develop. Now let's look at the difference between the structures of inorganic and hybrid perovskites. In inorganic perovskites, part A contains inorganic groups, while in hybrid perovskite, part A contains organic groups. The instabilities of hybrid lead highlight perovskites under moisture, heat or light seriously limited their applications as long-term devices. To remove the instability barrier for their applications, various strategies are proposed. Among them, replacing organic compound by inorganic one is the most promising one. For example, cesium lead halides demonstrate long-term stability without sacrificing any photovoltaic and optoelectronic properties. I will talk about the synthesis phase of the structure. It is divided into two as solid-state Bridgman method and solution method. In the Bridgman method, the precursors are melted at high temperature in a quartz tube and cooled very slowly by passing through a multi-temperature furnace. The Bridgman technique is costly because it requires high temperature, high vacuum and extremely pure precursors. Within the scope of the study, we use the solution method because of the advantages it provides in the laboratory. I would like to briefly talk about solution method, inverse temperature method, slow evaporation method, anti-solvent method, top-seeded solution growth, and bottom-seeded solution growth. Cesium lead halide structures has four polymorph. These are cubic, tetragonal, orthorhombic, and non-perovskite structure. Cesium lead bromide crystallizes in the orthorhombic space group at room temperature and transforms into a tetragonal phase at 88 degrees Celsius and a cubic phase at 130 degrees Celsius. In addition, cesium lead bromide has a wide band gap of 2.3 electron volts. In the table, you can see millimeter-sized cesium lead bromide single crystals obtained by different solution methods. At the end of the table, you can see a centimeter-sized crystal. However, the quality of the crystal did not increase proportionally with its size. So we can say that obtaining high-quality large size cesium lead bromide crystals by optimizing the growth conditions of the solution method is still a challenge. We hope our study sheds light on this challenge. There are some parameters that we try to optimize within the scope of the study. These are the ratio of starting materials, solution and anti-solvent types, temperature, cooling rate, environment, and amount. I will talk about these parameters respectively. The phase diagram of cesium bromide and lead bromide supports the formation of three compounds. This stoichiometry must be precisely designed to ensure the specific formation of cesium lead bromide and suppress all other phases. This cesium lead ratio was determined as 1.45 so that the resulting product could only be cesium lead bromide. Thus, rich in cesium bromide or rich in lead bromide phases were avoided. Another parameter we need to check is the solvent type. Here I will talk about commonly used solvents. In the solution method, this summary of which I have shown in the table. Mostly aprotic polar solvents were used to synthesize completely inorganic perovskites, and crystals with the desired transparency could not be obtained. Hydrohalic solutions were mostly used in the synthesis of hybrid perovskites, but it was not found to be used in the synthesis of cesium lead bromide. Therefore, hydrobromic acid is used in our study. In the literature, aprotic polar solvents have been used to obtain cesium lead bromide. When aprotic polar solvents are used, we see the graph of the variation of solubility with temperature. This solubility decreases with increasing temperature. When we look at the solubility test using hydrobromic acid, we observe that the solubility increases with increasing temperature. Thermodynamically speaking, single crystal formation and growth are promoted in a narrow solute concentration area at a specific temperature. For this reason, solubility plots were created for cesium lead bromide crystals in hydrobromic acid. By determining the required amount of precursor at a specific temperature, the formation of multiple nuclei and polycrystals was avoided. In this work, precursor solutions were prepared for a particular working temperature in order to redisturb any accidental nuclei formation. Then the precursor solution was gradually cooled to the working temperature. It is important to be able to control the experimental environment. Therefore, the experiment was carried out in small vials since small volumes were used. If we examine the cooling rate, the crystal size depends on the solution cooling rate. If the cooling rate is slower, slow nucleation takes place and large crystals are formed. With this in mind, a slow cooling rate was applied. Single crystal growth experiments were carried out at the solution nucleation limit under constant temperature or controlled cooling conditions. First of all, I will talk about the experiments carried out with the controlled cooling method. Seed and seedless experiments were carried out in the controlled cooling method. In the seed-added experiments, growth was observed in accordance with the morphology of the insert seed. But foreign nucleation could not be prevented. We want to prevent foreign nucleation because if we avoid nucleation at the bottom of the vial, growth will only be on the seed. Despite foreign nucleation, 5 mm cesium lead bromide single crystals were obtained in 5 days. In the controlled cooling method, nucleation is more controllable when the temperature range is small. As the temperature range increased, it became more difficult to control the nucleation, and many small crystals were observed. Constant temperature experiments were also carried out, seed and seedless. When we examine the nucleated constant temperature experiments, we see that approximately 5 mm cesium lead bromide single crystal was obtained in 10 days without foreign nucleation at 60 degrees Celsius. When we look at the constant temperature experiments with seed added, we see that foreign nucleation is prevented. Growth was observed only on the inserted seed. As the added seed size increases, the size of the product obtained will increase in direct proportion. If we compare the constant temperature and controlled cooling methods, the nucleation is more controllable as the constant temperature method reaches saturation more slowly. Constant temperature is the equilibrium state. Although a very low cooling rate is used in the controlled cooling method, the equilibrium is disturbed and nucleation is triggered. At high temperatures, defects in the single crystal became visually apparent due to the thermal energies of the ions. Defects can be observed much more clearly in single crystals at 80 degrees Celsius. These defects are also evident on the crystal surfaces of single crystals obtained at 60 degrees Celsius. Due to the relatively lower thermal energy at 40 degrees Celsius, the resulting single crystal is clear. In conclusion, it has been shown that pure, clear cesium lead bromide can be synthesized in a hydrobromic solution using constant temperature and controlled cooling techniques. And it has been shown that the seed added to the fresh precursor solution in the constant temperature method can be grown without foreign nucleation. Phase transitions at 88 degrees Celsius and 130 degrees Celsius in the differential scanning calorimetry plot confirm the cesium lead bromide single crystal structure. The X-ray diffraction of cesium lead bromide we obtained shows that it has an orthorhombic structure. X-ray fluorescence spectroscopy results confirm cesium lead bromide stoichiometry. Since the X-ray fluorescence technique is a more superficial technique, although the values are slightly lower than the energy dispersive spectroscopy measurements, it is understood that the ratios of cesium and lead in a single crystal are very close to 1. The excess of cesium is ideal to be because of the 1.45 of cesium lead in the precursor. We would like to thank Bursa Technical University Scientific Research Project Unit and Central Research Laboratory for their support. If you have any question about the presentation, you can contact us. Thank you very much for listening.